we asked someone to play Camerling on us, and we created a fake lab with the old lab behind, so people would go around and talk to him. Of course, there is a physicist nearby, Ricardo, for those who know him, Ricardo Lobo, to correct the answers. Because at the end of the day, the guy was very sure of himself, he was answering to everything. We had kids levitate, and we showed you later after that, but this levitates at about 2 centimeters, and then we gave them the official diploma of levitation. We went to high schools about 200 times this very year, and we keep on doing that, and we have done that for many years. So this is me, for example, in front of the high school using a hula hoop superconducting. I'll show you near a moment. We went to science museums, and they said to us, go away, we don't want to speak about quantum physics, it's just impossible. So we said to them, we're going to do it together, and then it worked. For example, this is in Cité des Sciences, which is the first French museum, and this is the very special place for the kids between 6 and 10. And they made a show for 2 months long, 4 times a day, on superconductivity in that very place. And it worked very well. They also made special animation. This is again a fake lab, and what is interesting is if you have a researcher, this is Frédéric, who is a researcher of the field, and a science explainer from the museum. And they are together to talk with the audience, so that the researcher is more confident and can tell about his own life, and the science explainer is there to correct or to lower the level. There were some amazing plays. This was a play given at Cité des Sciences again. We also tried to train the teachers for them to be able to do that in their schools. We also went back to our own universities doing the stuff to our students, which is I think, very important and which we forget too much. So for example, this is a Moebius ring of magnets where you have a levitation of a superconductor on it, and these are just university students. And then we tried to explore other ways. Remember the media. The media was really a problem. How to go again to the media and to tell them, oh look, I have my levitation. And they would tell, no, we did it 10 years ago, we don't care. This is an important step because we realized that if you don't have the media, then perhaps the large public will not come to your events, even if you have organized a marvelous event, and we wanted the public to come. So I'll show you how we succeeded to seduce them. We began to think, what can we do better than that? This is already amazing, but what is amazing is that you have levitation, but you can do it the other way around, and it says stick. This is what we call pinning forces, and it's really amazing. But still, we wanted to do better. So the first thing you can do, and we have done that for years, is to create, this is an old movie, sorry for the resolution. So we did a setup where you will have magnets, and you have a small glass which contains a superconductor. The superconductor is on the bottom of that small glass, which is full of liquid nitrogen. So it levitates and it floats on the magnets. But at the same time, it stays pinned. So you have this levitation, but then you can play it all the way around. And this is very useful because you can bring that to any high school you want. You can put it in a suitcase. So this is me a while ago in my lab. And as you can see, it can hold. And it's not just the movement. You can put it anywhere you want. It will hold as long as it is cold, of course. So that's very easy to build. I mean, you need about 100 euros to do the full setup. And as long as you have liquid nitrogen, you can do it everywhere you want. And it's wonderful. But this still was not enough for the media. And then the CNRS agency told me, okay, we have the opportunity to have a special place in front of the Eiffel Tower for 2 weeks. Do you want to do something there? So we decided, we have to do a superconducting Eiffel Tower. So this is what we did. So each floor levitates with liquid nitrogen on top of superconductors. And this is really the Eiffel Tower behind. And so you feed it with liquid nitrogen in front of the audience, and you do it, 10 times a day. At the end, we have put a LED to have some lights on night which would turn, like the true Eiffel Tower. And then if you have that, you can have many people coming, you can have the media coming, everyone comes because, wow, there's a levitating Eiffel Tower. So for example, this is us in front of the Trocadero, and the picture I showed you before. We had 20,000 people coming on a weekend to see that. And then once they are here, you can talk to them about quantum physics, and they agree to stay for about half an hour hearing you speaking about quantum condensates. We thought we should do better, so we did this magnetic surf. So it's like Back to the Future. This is full of liquid, of superconductor. This is Alain Sakuto, one of our researchers. And these are magnets. And so you see that your magnetic surf, your superconductor magnet surf, will float on the magnets. And you can put anyone you want on the top of it. And believe me, I tried it. Basically, you fail. Because there is no friction anymore. So we had a teenager who said, I'm doing surf, I can do it, and they would go. So finally we put protections to anyone who would do it. Recently, Will Smith used that one in a TV show. So we are very proud of that because we have one of your Hollywood stars using superconductivity live on TV. We had also the issue of how to engage kids, because if you want to do quantum physics with kids, it's not that easy. And the problem with these experiments is that you have liquid nitrogen, so it's very dangerous. So you cannot leave them playing with it. So we wanted to find something for them to do for these big festival, big parties. So we created some folding activities. So this is the way, for example, to fold a superconductor. So you start with that you can print in your room, or that we bring it for you. And then this is my daughter again doing it. And at the end of the day, you end up with understanding what is a superconductor, because that is your superconductor, that is your superconductor, that is your magnet. The magnet creates magnetic fields line, which are expelled from the superconductor. They cannot enter in the superconductor, and that makes the thing levitate. And once they have done that, they bring it with them, and you show them the real experiment, and they are able to explain it to their parents. And look, it's because you have lines that you don't see which are invisible, but I made them, etc. The next thing is that also they come back at home with something. With that, we made also many different stuff. We made them working with atoms. So that would be an atom, that would be another atom. For the specialists, it's a Z square R square orbital. And we will ask them to do that with specific, models. This is electrons with electric currents. So you can see the scattering of the electrons. And this is Cooper pairs. You don't have scattering anymore. The current flows very nicely now. And that's a superconductor, and you can build it on your own. You can download everything on the web. And that's the one I showed you. Finally, we went to a design school, industrial design school, and told them, help us to do new stuff. We have no idea what. We give you the levitation, we explain to you a little bit the physics, and work with that to do nice objects, and to imagine also other objects. The idea was to ask them two things. First is, do nice objects so that we can replace our usual hula hoop or train. And the other question to them was, what would be the future if we didn't have to cool the superconductor anymore? I had imagined electric wires and stuff like that, but I asked them, could you imagine something else for us? So first they did object. This is, for example, a sculpture, which is held from below, which is held to nothing. There is vacuum, and if you make it turn, it turns in night with very nice lights, and it turns very long because there is only the friction of air. And you have liquid nitrogen on the top of that. This is a superconducting circus. So you have a circus that you open, you have many animals full of liquid nitrogen, which create amazing stuff. This one, for example, you can see the videos on YouTube. This one makes a French cancan dance on the top of a device speaker, and where there's a superconductor on the bottom of it. There's a magnet hidden there, and there's a speaker hidden, and you play French cancan, and it will move in rhythm by induction. So it's really nice. And many other stuff like that. And then we ask them, think about the future. So I could ask you the question, if I would allow you to use superconductivity, levitation, also levitation upside down, what would you create? So here are the answers. The first one is very simple. You don't burn yourself anymore if you take a hobby. So this would be made of magnets. You would have superconductors here, and you can hold without touching your plate. Of course, then you should put magnets in your table as well, so that the plate will not burn the table because it will not touch it anymore. Then, as we are in Aspen, here is the sport superconducting line. So the idea was, if you were to have textile made of superconductors, what could you do? So what the students invented is a sport. So each thing in black, you have to imagine that it is made of superconductors. There is some sound for that.
Oh, no.
So as you can guess, you have no friction anymore. It holds, but doesn't touch, which is very nice. You see, we made it in English also as well. For those who do hike trails nearby, this is really nice. So, if you have to think, of course you don't lose the weight of the backpack. Physics still tells you that there's a force, but there is no more friction with your back. So the other one I wanted to show you is Jewels. That's a nice one. In this one, as in the other one, we didn't play completely science fiction. We just said to the students, stick to reality in terms of distances, weights, etc. don't do the absurd stuff. And they really tested with liquid nitrogen that it would work. And then we told them, once you have tested it with liquid nitrogen, show us what would be the future. So that would be the future of J-wells. So your superconductor would be below, that black powder, and the J-well should be magnetic. If you do that, then you can create a cream made with superconductors. And then on the morning you decide where you want to put your J-wells. So I asked that we should see the wire. And of course, using that, you can imagine very nice ways of reinventing the J-wells with the shadows. This is the one. For that, you really need design students. I mean, even better, you can play the hula hoop story. Namely, you now create a magnetic cream with all the magnets aligned the same way. So if you do so, your superconductor will be able to float on them like the hula hoop. So you create the shape you want in the morning. This is your superconductor. Okay. So if you want to see other future videos, there are many of them on the websites. I will tell you after that. There are many, many funny to see. What have we learned from that? We have learned a few lessons that I want to share, especially with the physicists here. The first thing we learned is that large public is not afraid of physics, even if it's pure quantum physics. This was not obvious at the beginning of the story. I knew that it was the case because I had gone in many high schools, but the other researchers were not convinced by that. But once you do it, you realize that everyone is curious and interested. Also, everyone has told us if it has no big applications, people are not interested. I think it is not the case. All the questions we had were not about the applications, were about liquid nitrogen, quantum physics, cold temperatures, what's happening, etc. People are much more curious than we think. The other lesson we gathered from that is that it is important that researchers themselves play that game and are here in front of the public, because it is not just what you explain which matters, but also who you are and what you can tell about research and your daily life. And half of the questions we had was about what is a lab, what is a physicist, what are you doing in the morning, etc., etc. So I think it's very important that researchers are involved in that process. Also, we realized that sometimes outreach activities, it's one researcher who does it on its own, doesn't want to tell too much to the colleagues because they would think that he doesn't work enough. The fact of being all together doing that is much easier because the look of the other changes because everyone is involved, and that helps a lot. So being a lot of us together was very helpful. And here it's just scientists. For those who know, this is Dimitri Rodichev, this is Mario de Measson, Benoît Fouquet, all specialists of superconductivity. We learned, as I showed you, that it's very important to find new ways to show the physics, because then the media come, then the public come. Telling to people, come and you will be able to levitate on a magnetic surf, made many people come. We did, for example, a superconducting party in Paris for a day where it was rainy, and we had 5,000 people coming just to float on the magnetic surf. And once they are there, then you can show them all the rest. We also found out that it's very useful to create websites, to create animations, to create wiki articles, all that stuff which will be usable for anyone on Earth, and that it will stay even beyond the year 2011. So we tried to do so. And last but not least, I think the big thing that everyone learned from that is that it is fun. For all those who didn't do it before and tried it for the first time that year, they realized that it is really fun to engage with the public. And that's what we realized, so that's again linked with the superconductivity. In terms of perspectives, I'm not speaking about science now, I'm completely on the outreach side. What we try to do now is to have all the institutions, the universities, etc., a knowledge that work in various ways, like in our teaching duty, for example, or in our promotions. We also try to expand everything we have done on superconductivity to the whole quantum physics. That's a challenge, but we realized that not that much was done up to now, so we are trying to do it step by step. So now we are doing very nice animations with the help of ICAM that you can see already on the web. I showed you 3 of them: duality, orbitals, this is a microscope, tunnel effect microscope. And we're going to do a website, and we are again collaborating with that design school to now do quantum physics with design, and we're going to see what happens. And so we try to do new outreach resources and activities about quantum physics. We did a quantum day in Paris 1 month ago where we had again 4,000 people, and we said to them, we're going to speak to you only about quantum physics, and they came. And finally, I think it is very important to exchange, that's why I'm here in this wonderful conference that you organized, David. And it's very important to share the resources, to share everything we do, because you are doing amazing stuff in the United States. I have many of them today. And I think it's very important to exchange best practices, because there is no competition. We are all in the same boat somehow. And it's not like just like science where you want to publish before the other one. If you have a magnetic surf in the United States and I have a magnetic surf in France, very well, everyone is happy. So I tried to summarize that in a final picture, and I thought, what could I find, like a link between France and United States and superconductivity and quantum physics? So this is a replica of the Statue de la Liberté in the Musée des Arts et Métiers where we did this quantum day, and so we were very proud to have the small Eiffel Tower in front of the large Statue de la Liberté with liquid nitrogen and levitation, but we didn't make it levitate yet. So all the possible resources, videos, folding activities on quantum physics and superconductivity, etc., are on that side. Vulgarisation means popularization in English. So you have learned, and I thank you for your attention. So if you want to engage the dialogue on any possible topic, yeah.
When you have a magnet levitating above a superconductor, is the distance of the levitation related more to the strength of the magnet or some property of the magnet?
That's a very good question. That question was first asked to me by a guy about the Avatar movie. The reason why is that, I don't know if you saw that movie, but in Avatar you have floating mountains which are supposed to be magnets on top of room temperature superconductors in the story, they tell so. And the guy was wondering, would it be possible one day to have floating mountains at 100 meters from the ground? So we did the math. And basically, what matters is the strength of your magnets. And it will be more or less proportional, the height, to the strength of your magnets. So the higher your magnetic field is, the higher it will go. And so we computed in Avatar what should be the magnetic field to have these mountains, and we found out 10,000 Tesla, which is just an impossible field because all the matter will break at that field. So Avatar is impossible and will ever be impossible. But we could increase the height here if we were to put larger magnets here. But we will perhaps increase it by a factor of 2, not that much more. Because then you need really big magnets that you can have in labs, but that you cannot carry with you without danger. Yeah?
What is the latest high temperature, the highest temperature that's been reached with superconductors currently?
Okay, it's not very recent, but without any pressure at standard atmosphere, that would be about 134 or 35 degree Kelvin. So it's in Fahrenheit, I don't know how to convert.
So
it's still cool.
Have not changed recently?
No.
Not too bad.
Yeah. Yes?
That's a very big educational component. So is that a national project in France, and who runs that project if it is?
No, we started locally in Orsay. I mounted a team and we went to high schools, etc., etc. And then when this year, 2011, happened, the CNRS French agency asked me for 1 year to take in charge the whole stuff. So she paid for my teaching duty so that I would not have to do teaching for that year and I could do just research and outreach. So then the CNRS organized all that through our actions. But that's it. But I have to be honest, all these initiatives are more or less local. And we want to maintain them that way. We don't want to have a big national program. We prefer that we have local engagements and then we gather all of them in common resources and we help everyone. But we think it's better that everyone locally plays its own game.
Thanks.
Yeah.
Can you explain again, you showed that blue field, and you showed the 2 electrons moving, and then you saw the field. What happens between the 2 and the stronger field?
Okay, so you're speaking about the blue wave. Okay, so what happens when the metal becomes a superconductor is that the electrons will go 2 by 2. Okay, so they will make this pair, and that pair, because of its movement and the way it's arranged, if you treat it quantum mechanically, you will find out that it creates some kind of a larger wave than the 2 components. So that's that big wave that I showed on the top of the 2 electrons. That wave, we know how to measure its size. It's still small, but it's much larger than 1 electron wave, okay? So, but that is not enough. What you need then, if you want this huge final wave, is that all these pairs, which have their own waves, will superpose to each other perfectly. That's what's happening in a laser, for example. In a laser, you have all these grains of light, which are called photons, which have their waves, but which superpose perfectly. And that's what makes the light of a laser so specific. So I would say that a superconductor is a little bit like a laser to a standard light. That all your electrons we'll first couple 2 by 2, and then we'll coherently create this gigantesque wave. The tricky thing is that in superconductors, usually the two happen exactly at the same temperature. You don't have first the pairing and then the big wave. The two of them happen at the same temperature, at least in the old superconductors. Yeah.
How did you come to the idea that you wanted to devote some of your time to this very impressive?
That started, for many of us, that started in year 2005 because it was the International Year of Physics. And so everyone said, okay, this very specific year, let's try to do something. So I tried to do a talk in a high school, and I realized that they love to see live experiments. And so then I devoted time to mount a team for just high schools, small scale, locally. And then we saw that it worked very well, and then we could expand. But it's not like a big decision for a big national scale right from the beginning. It's small stuff that progressively extends, and many more people come to the game once they see that it works, and at the end you have many people involved. But it started like 2 of us creating small hula hoops in the lab and going to the nearby high school.
You've obviously had a lot of support for this, then, because it's fabulous. As an old middle school science teacher.
Well, at the beginning we didn't have any support and we hid it. Because once again, your colleagues think you lose your time doing that. And it's just after a few years that they realized that we are bringing students in the university. And then there was this national year where everyone accepted to devote a part of his time to that. But it is not so obvious among the researchers to do this kind of activities, I would say. But we are here in this conference to try to convince other researchers to play that game.
So it's been a great talk. You've been a great